Okay, so let's prove the fundamental theorem of arithmetic, second part. What does that say? It says that when you factorize a number into a product of primes, you can do this in, at most one way. So that there's only one collection of primes that when multiplied together equals some given number, for example, 20. So 20 is 2 times 2 times 5, and there's no other collection of primes that equals 20. Okay, so let's prove it. So the fundamental theorem of arithmetic, part 2. So part 1 was that you can, factorize any number into primes, and now we're showing that it can be done at most in one way. Okay. So factorization is unique. Okay, and ultimately this boils down to a very simple extension of this GCD fact number 5, okay, which says that, so lemma, remember this thing lemma? So a helper theorem, a helper result. If a prime divides a product, then it divides one term in at least one term, then it divides at least one term in the product. So what does that mean? If a prime P divides Mn, then P divides M or P divides N. If prime divides product, it divides one of the terms. Then you can generalize this to any number of terms in the product, and I ask you to do this by induction, and you should be able to, do it by induction after I show you how to do it for 2. Okay? So if a prime divides a product, okay, so suppose P divides M. If P divides M, then we're done. If P divides N, so proof. If the prime P divides M, we're done because it divides one of them. So you're done. Okay, if P does not divide M, so if P does not divide M, okay, that means M is not a multiple of P. Okay, so that means P is not a divisor of M, and there's no other divisor of P except 1. Okay, so that means that the greatest common divisor, this means that the greatest common divisor of P and M equals 1. But if the greatest common divisor of P and M equals 1, then it means that P divides N. That's exactly what we proved. If the GCD of D and Mn is 1, if the GCD of D and M is 1, then D divides N. Okay, so if P divides M, we're done. And if P does not divide M, then its GCD with M is 1, in which case, by GCD fact 5, it must divide N. Okay, and so therefore, if it doesn't divide M, it divides N, so this OR is always true. Okay. An interesting sort of, and the way we're going to use this fact is that if P divides, let's say, Q1, Q2, and both of these are primes, okay, then P is one of those primes. If these are all primes, then P divides Q1 or P equals Q1, P equals Q1 or P equals Q2. And, why is this? Because we just showed that if P divides a product, it divides one of the terms. So it divides Q1 or it divides Q2. But Q1 and Q2 are primes. So the only way P divides Q1 or Q2 is if one of them is equal to P. Okay? And again, you can, by induction, extend this to any number of, primes in the product here. Okay. So I'll just summarize that, and it's for you to prove by induction. If prime P divides Q1, Q2 up to QR, then P equals Qi for at least one of the primes Qi. Okay. So, we just did some sort of deeper investigation into GCD fact 5. Basically, if a prime number divides a product of primes, then one of the primes in that product is my prime number, P. Okay. So now let's come and prove that prime factorization is unique. Well, we're going to prove it by contradiction, and we'll take out our fishy pen, Okay, because we're going to prove it by contradiction, and we're going to assume that no, it's not the case, that there is some number which has two different prime factorizations. Well, if there's some number which has two different prime factorizations, then there's a smallest number which has two different prime factorizations. We're talking about positive numbers here. Okay, so let n star be the smallest positive number with two, and I'm going to emphasize different prime factorizations. Okay, so n star is equal to p1, p2, p3 up to pk. Okay, where and also n star is equal to q1, q2, q3 up to qr. So they're different prime factorizations. So they don't even need to have the same number of primes. And they're different means that at least one of the q's is different from one of the p's. Okay, and all the primes are bigger equal to 2. Okay, so p1 clearly divides n star. So p1 divides n star. So if it divides n star, well, it divides n star because they're the same number. Okay, so that means that p1 divides q1, q2, q3 up to qr. But we just argued that if a prime p divides a product of prime, then at least one of these is equal to p1. So this means that at least one of these equals p1. And, you know, without loss of generality, okay, so we can assume, we might as well just set that the one that equals p1 is q1. It could be any one of them, so it could be q3, we can just relabel. We can relabel q1 to q3 and q3 to q1, okay, and then p1 equals q3. So one of these is p1, we might as well assume it's the first one. So that means that n star is equal to p1, q2, q3 up to qr. Okay. And, you know, we have that now p1 divides n star. Okay, so let's look at n star divided by p1, which is p2, p3 up to pk. Okay. Let's look at now n star divided by p1 in this representation. So then n star divided by p1 is equal to q2, q3 up to qr. So the first observation we have to make is that, well, you know, can this number be 1? If this number is 1, it means that this number is 1. It means that n star equals p1 and n star equals p1 are both, so these numbers are, they don't exist. That means that, you know, these numbers are all 1. They don't exist. So r equals 1 and k equals 1. So this number is not, if this is 1 and this is 1, then n star equals p1 and n star equals p1. They're not different factorizations. So we conclude that this number is not 1 and this number is not 1. So these numbers are strictly greater than 1. But the important thing is, these numbers are greater than 1. But the important thing to note is that since the original prime factorizations are different, the only place they can be different is in the terms p2 to pk. So these terms p2 to pk cannot be the same terms as q2 to qr. Okay. So what that means is that n star over p1 and is equal to, you know, p2 up to pk, and it's also equal to q2 up to qr, and these are different prime factorizations. Okay. And if they're different prime factorizations, then how is it possible that the number for which they're different prime factorizations is less than n star? Because it's n star divided by p1, and p1 is bigger than or equal to 2. So this guy has different prime factorizations, and it's smaller than n star. Smaller than n star. But n star was supposed to be the smallest, so that's fishy. Okay. And that means that this n star cannot exist. N star cannot exist. And what does that mean? That means that there is no number which has, no positive number which has two different prime factorizations. That proves the part 2 of the fundamental theorem of arithmetic.